Hi everyone, I'm Tyler, and I'm going to talk today about inference for partially observed network data. And this is a really broad topic with lots of interesting open areas for future work and for ongoing work. So I'm going to try to give a broad overview today. There's certainly things that I won't be able to cover in the depth that they deserve, and there are lots of, like I mentioned, sort of open interesting areas to explore more. So I put my website at the bottom right here. Feel free to reach out. My contact information is on there. Please feel free to reach out with questions that you might have after this presentation. Okay, so today what we're going to do is I'll first sort of talk a little bit about sampling strategies for networks. I'll sort of dive right in then to the implications of sampling for inference, and then I'll talk in detail about one particular way of sampling, which is called aggregated relational data, which is in some sense a sort of an extreme example of partially observed network data, but I think that it illustrates sort of some of the broader principles that I'll talk about in nice detail, and allows us to sort of talk through some examples with some specific data. Okay, so first let's think about sort of how we go about sampling from a network, and so the kinds of questions that we might want to ask. And so here I've given you sort of one very particular sample, one kind of sample from the network, and ask a sort of set of questions over here to the right-hand side. So how many clusters are there? What's the length, the longest path? And sort of how would you sort of characterize the amount of clustering in the graph? And so you might be able to see some signs here that I've kind of done an amateur job of sort of photoshopping or cropping this picture from a larger graph. But that notwithstanding, I would argue that sort of without knowing anything about the sort of sampling strategy here, it's incredibly difficult or essentially impossible to answer any of these questions. You can answer them about the sort of the part of the graph that you've seen, but it's really impossible to know what how you would infer any of these questions without seeing the rest of the graph. And so this is the picture that the graph comes from, and so you can sort of see that from the longest path to the sort of description of clustering, the way that we do sampling is really fundamental in sort of understanding the sort of types of relationships or characteristics that we might or might not be able to recover. And here's just another illustration of that. So this is a graph where, if we imagine the sort of the strategy to the left here, where we're sampling smaller sets of individuals from various parts of the graph, compared to the strategy on the right, where we're sampling here in the red circle, one sort of large dense community. You might imagine that the sort of statistics that you come away with, the sort of characterization that you come away with from the graph, is going to be radically different in these two settings depending on the sampling strategy. And this is obviously a sort of very high level, sort of simple illustration, but I think brings across the point that that the strategies that we're interested in here, the strategies for sampling, sort of are fundamentally tied to the kinds of information that we can recover. And what we observe about the graph gives us a sort of partial picture of the complete graph, and the characteristics of the network, the sort of dependent structure, the multivariate dependent structure that define the links in the network, also are critical for understanding the sampling process, right? So you might imagine that something like a simple random sample of nodes is going to give you a very different idea of what's going on in the graph than a sort of purposeful sample of one of the clusters, right? So something where you're, for example, identifying groups of people, say based on a sort of common location or common characteristic, and sampling everybody there, it's going to give you a sort of very different perspective on the graph, and the sort of underlying features, the sort of structure and properties and characterization of the graph that we're sort of fundamentally interested in. That's going to sort of also explain why sampling is a challenge, right? We need to sort of sample people in their context in order to appreciate some of these sort of properties and higher order features of the network. Okay, so there's a couple of sort of common sampling strategies that I'm going to talk about today. And the first part of this talk, I sort of have credited the figure at the bottom here from this paper from Chandrasekhar and Lewis, but essentially most of the first part of the talk is going to be drawn from insights from that paper. And I'll give the sort of the full reference at the end as part of the slides. But a couple of common strategies here. The first is in the sort of top panel. So here's our complete graph A. So this is the object that we want to, in panel A, this is the object that we want to sort of do inference about. So essentially the idea here is that we're going to start with a sample of nodes, and with this sample of nodes, we can construct the sort of first type of common type of sampling approach that people use, which is to construct an induced subgraph. And so this is essentially to sort of start with a sample of nodes and then trace the connections among the selected nodes. Right, so we're going to take a sample of nodes, and then we're going to trace the connections amongst those nodes that we select. And so you can see here that, for example, so we're only allowing connections in this induced subgraph. We're only allowing connections that are between individuals who are in the sample, right? So here we do see some triangles, right? Because we have 3 individuals here. All 3 of them are sampled in the set of nodes that are sampled, and we match the edges between those. Okay, so another sort of common form of sampling is what's called a sort of star subgraph. And in the star subgraph, we're going to get a bit more information than we do in the sort of induced subgraph, because we're going to take a set of nodes that are sampled, and then of that set of nodes that are sampled, we're going to look at all of the connections amongst the nodes that are sampled. So that's going to allow us to either sort of directly or indirectly, and typically the latter. It's going to allow us to sort of trace connections between individuals who are included in the original survey, the sort of nodes that are in red here, and others that are not. And so if you see here this sort of induced star subgraph with the sort of nodes highlighted, you can see here that this node is blue, but we've included the blue node here precisely because it's connected to, in this case, 2, but at least one of the sampled nodes, the nodes that are in red. Now you notice that this particular node here, if we trace back over here to the sort of complete graph, this node here there's also an edge between these 2 nodes. But you notice that in the star subgraph case, that edge is not observed, because the sort of the second blue node here, if we call this one B, and if we call this one A, so node B here doesn't have any connections with people who are in the sample, and therefore we won't observe any connections with node B, because that person doesn't have any connections with individuals in the sample. And so similarly, you can see sort of another implication of the star subgraph type sampling approach here. So here's a node that is included in the sample. So this is a node that has been sampled. So we learn about 2 connections that this person has. So a connection to this node here, and then a connection to this node here. So those are individuals who, again, we learn about some of their connections because they're connections with people who are in the selected set of nodes, but we're not learning about the connections between those individuals. And so if you isolate, again, the same sort of piece of structure over here, what you see is that there's actually a completed triangle here, right, between the sampled node and these 2 unsampled nodes. There's actually a completed triangle, but we're not going to observe the completed triangle because one of the edges in the triangle is happening between nodes that are not in a sample. Okay, so in the star subgraph, we're going to see the connections we're going to see the connections from people who are sampled, in this case, the nodes who are red. And so we're going to get some information about the connections that those people have with individuals who are not in the sample, but we're still going to be missing edges that are associated with people who are not in the sample, right? Because those, if those edges take place between two people who are not in the sample, we're not going to observe them, right? And so examples of that would be the edge between A and B here, which I pointed out before, and then this sort of completed triangle, right? Where there's an individual, there's the sort of an edge that's missing to complete this triangle that's not observed because the final edge happens between two people who are not in the sample. And so, so this sort of triangle is a great example, right? Because if you were trying to do something like a count of the triangles, then even if you have the induced subgraph where you're only looking at connections among the selected nodes or among the sampled nodes, that's going to sort of clearly give you a misrepresentation or a sort of a relatively low quality estimate of the number of triangles in the graph. But even if you look at the star subgraphs, you have a little bit more information. You're still missing sort of critical elements that are needed to sort of to count the number of triangles. And so that's going to be kind of a theme here throughout, is that the even in the sense of that the sort of star subgraph gives you a bit more information. It's still sort of challenging to address this this sort of missing data that occurs through sampling. Okay, so those are the two sort of strategies that are that we're going to sort of mostly focus on. We'll introduce a third strategy with this aggregated relational data, but that's kind of a bit of a separate separate topic that we'll come to towards the end. Okay, so what are the implications? And I should mention here that there are, this is sort of thinking, these are sort of two common strategies where the goal, where we're thinking about a goal being to sort of learn about or sort of estimate some of the features of the network. There are other strategies that we could pursue where the goal is not necessarily to learn about features of the network. That may be a byproduct, but the goal is not necessarily to learn about features of the network. So things like respondent-driven sampling or link tracing designs are certainly sort of ways of collecting partial network data, but those are typically not necessarily employed to learn about features of the graph as much as they are to learn about sort of features of a particular population or a particular group, or to sort of to reach particular members of the population. Okay, so what are the implications of sampling for inference? So just to sort of talk about our general goals here, we want to, I'm thinking about the setting where we want to do something like compute statistics from the subgraph, and then use those statistics in something like a regression model. And again, there are lots of other settings that we might think about. We won't necessarily have time to sort of go through them in this sort of quick overview, but there are sort of other goals we might have. But for the purpose of this lecture, we want to think about computing statistics from the graph and then using those statistics in something like a regression model. So the key point here is that even if the nodes, the individuals, are selected randomly, partial sampling leads to non-classical measurement error, and therefore to bias and regression coefficients. And so this is not necessarily attenuation bias. This could be bias in a positive direction or a bias in a sort of negative direction in terms of the sort of size of the coefficient. So, so that's the sort of situation that random selection of the nodes, while appealing in some respects, is not going to sort of get around the issue of bias in regression coefficients. Okay, and so I'll talk more about that in the next few slides. So just to be more specific, let's say that a researcher wants to fit a model where the outcome of that model is some value y. We're going to assume it's continuous here just to make things a little bit simpler. The predictor function that we're interested in has a statistic on the graph. So we have a graph G here. So this is the full graph G. And this omega represents some statistic. So maybe it's a clustering coefficient, maybe it's a sort of triangle count, maybe it's a sort of average degree. This represents some statistic on the graph, and I'd like to model the outcome y as the function of the statistic on the graph. And so the setting that we're going to think about is a case where you don't have access to the full graph, but instead you have access to either the subgraph, either a subgraph, so an induced subgraph, the connections between individuals who are, the connections between all of the sampled individuals, or a star subgraph. And so instead you run a regression that looks like this, where if omega g is telling you about the statistic on the full graph, omega g tilde is telling you about the statistic on the subgraph, either the star subgraph or the induced subgraph. And so this omega g and omega g tilde, they can either be graph level or individual level statistics, right? So, so if they're individual level statistics, you might be interested in how, how, for example, you might be interested in how, for example, someone's position in the network. So say, something about a sort of local, sort of individual level centrality measure relates to some sort of health outcome that a person might have, maybe a sort of, mental health illness, mental health index or something like that. And at a graph level, they could be sort of summaries of a sort of particular feature of the graph. And so say that you have, a number of different sort of distinct graphs. So maybe you have, maybe you sort of have data from an online wellness platform like Strava that has a social feature. And so you can sort of partition that graph into sort of individuals, sort of communities of people who are, who sort of work out together or work out, share their workout information with a small set of other people. And you want to compute things like, you want to compute sort of statistics like, say, maybe the sort of longest path or the average path length in a particular graph, the average degree of people in that graph, that sort of thing. And then you want to sort of compare those to an outcome. And so maybe in the Strava example, it's sort of the number of miles that that people bike in that network every week or something. So that's sort of the general idea, that you have a feature, some feature on the graph that you'd like to measure, and then relate that to a particular outcome through a linear model. So if you remember, under sort of a classic regression model setup, so sort of abstracting away from the network for just a minute, if we don't make any assumptions about the measurement error, so the measurement error here, and this is sort of in a this is sort of at a graph level regression. So R, for example, is your sort of Strava community. So so my friends in my subgraph that interact on Strava and report our sort of fitness and our workouts to each other is sort of one network. Your friends, your sort of group of people on Strava that you report your workouts to, that's another group, and so on and so forth. So under a classic setup with measurement error and no assumptions, then if we sort of continue to use this tilde as a mismeasured, as an indicator of mismeasurement, then what we wind up with is, what we can show is that that the sort of the limit of the estimator of beta hat looks just like essentially the sort of true value scaled by this term here, which has to do with the variance of the observed, so the variance of W tilde, which is the sort of corrupted version, and then the covariance between the actual graph, the actual sort of covariate, the actual X value, and the value that's that's observed. And so, to sort of just to kind of, in case this sort of formula doesn't look familiar, essentially where it comes from is basically just taking your estimate of the regression coefficient. So this is a single variate regression model so just taking the sort of estimate of beta hat in that regression model, and then substituting back in for that value of beta hat, to sort of to introduce this sort of actual observed effect as opposed to the W tilde effect. So essentially, this is just a sort of a manipulation of the sort of the regression coefficient, the estimate for the regression coefficient, that then allows us to that then has the actual value W substituted in as well. So the key point here is that this bias depends on the covariance between the estimated, the observed W tilde covariate and the actual covariate W. And again, this is the sort of fully general case, right? So this is not a case where I'm assuming that, for example, the measurement error is the error in the measurement error is independent of the true value of W, right? So like you might in sort of a classic attenuation bias type situation, or that or even in kind of your sort of Bergson type measurement error model, where the sort of there's an assumption about the relationship between the sort of error distribution and the sort of observed value of the statistic. So this is the sort of fully general case where there's no assumption here. And the key point here again is that this bias, so the limiting distribution of beta hat, the difference between that and beta depends on this covariance between the observed value of the regressor and the true value. And so this is really tough to sort of figure out what this would actually be. So typically in the sort of networks case, this covariance is not tractable. In some cases, you can sort of simplify it and think of it as basically a scale shift, right? So for things like degree or average degree and sort of graph clustering, you can kind of think about, essentially sort of leveraging the fact that the nodes are sort of randomly sampled, to sort of essentially think that sort of in expectation, if we think about degree, for example, if we reduce the number of people that it's possible for you to know, then you might imagine that the sort of expected number of people known in the network is going to be reduced by about the same fraction as the number of people who are, who it's possible to know. So some things like degree kind of work as a scale shift. Typically, this covariance is not tractable. It's not something that we know. But thinking about the case where it works as a scale shift, then essentially what we can say here is that we can sort of think about the expectation of the expectation of omega tilde, which is our observed quantity, conditional on the actual quantity, as just some sort of deterministic function of the sampling rate. So essentially sort of something that's going to basically scale up and down, some sort of scale factor, where that scale factor depends on the sampling rate. So if we go through and we use this sort of same process, so essentially just take this covariance and write it out in terms of expected values, and then substitute in this quantity here, where we're basically saying that the expected value of our W tilde, our actual observed quantity, is some scale factor times the real thing, plus some small remainder that we won't really talk about. Then what you wind up with is that the sort of limit of your beta estimate, your coefficient, now becomes a product of two things. The first is a scale factor, right? So that's the sort of, again, product of this sort of sampling rate, and it's that scale factor times something that's essentially representing the sort of classic attenuation, right? So the key here is that now we have these sort of two components that are kind of working together to give you the one term here, the scale factor, is sort of coming from the sort of sampling process itself. And then there's the sort of classic attenuation part, which is, depending on the sort of the variance of the thing that you're trying to estimate, the sort of the heterogeneity that you observe between the sort of individual values of the observed and its expectations, so sort of how much variation there is there, and then again the sort of scale factor at the bottom. Right, and so what this means, the sort of ultimate conclusion here is that has to do with the sort of the addition of this scale factor. So the sort of scale factor could sort of push up or down, right? Because remember, if we take the sampling rate as some value phi, then the scale factor, I mean, really what this is sort of some deterministic function of the sampling weight, of the sampling rate. But the key thing here is that this is not a function that that's sort of going to behave in a uniform way. So this could be something that either expands, introduces a positive bias, or sort of further attenuates, introduces a negative bias. And so what you have here is this sort of trade-off between a sort of classical attenuation bias type term that's sort of going to give you a negative bias in your coefficient, and this function of the sampling rate, which could sort of bias upwards or could bias downwards. The sort of the sort of values that you see. And just to give you an example of where it biases, where it could bias upwards. So for example, I'll give an example later on, or I'll discuss the sort of average path length. And you can sort of see that as you sort of thin out the graph, it's going to sort of serve as you sort of thin edges out of the graph. That's sort of going to, if you're interested in the sort of the average path length, as you thin out edges, then what you're going to do is sort of be taking out a bunch of the edges that are sort of representing many of the sort of shorter paths, especially if you sort of you think there are just sort of more of those in the graph. So essentially, what that's going to do is sort of as you sort of thin out the edges, it can sort of serve to give you sort of positive bias in this this sort of average path length, and so that sort of is an illustration of why we can't sort of just why we can't think of this bias that comes in, even in the sort of scale case. We can't think of this bias as sort of something that's always sort of serving like a sort of classic attenuation bias and making us underestimate our coefficients. It's also going to sometimes make us overestimate our coefficients. Okay, and this is sort of giving you sort of a recap of what I just said. There's two sources of bias: the scale effect that depends on the sampling rate, which can sort of either expand or attenuate the magnitude of the coefficient, and then a dispersion effect that generates further sort of classical attenuation. Okay, so I'll just pause here to note that I'm talking about this in the multivariate, in the sort of univariate case, but the multivariate case gets even more complicated, and so this is a case where we have two coefficients, where we have one is the average clustering, and that's sort of related for beta 1. So this is the average clustering, and the second is the average degree. This is a plot of the sampling rate. So the y-axis here is the sampling rate, both of these plots, and the sort of x-axis here is the correlation between these two statistics, between the average clustering and the average degree. And so this is the correlation on the x-axis here. And so the key point here is that this coefficient, the average degree, is not measured with error in this simulation. Right, and so this is the sort of the heat map is sort of giving us the values of values of the coefficient. And so what you see here is that for the first one, so for the average clustering, about 2.5 is the sort of true value. So the sort of green represents true value, blue represents sort of bias to the negative, red represents bias to the positive, to the larger effect. And so in the second case, the average value is about 10. So again, same thing. Green represents positive, and red represents positive bias, blue negative bias. And so what you can see here, so remember, so this is a regression, right, where the outcome is just y is beta 0, 1 average clustering plus beta 2 average degree. Right, and here the average degree is not mismeasured. And so why is this a particularly pertinent example? Well, if you sort of scroll back a few slides and you remember what we talked about with this star sampling, this star subgraph sampling, if we're measuring all the links that come from, if we're including all the links that come from the sampled individuals, then we should have a pretty good estimate of the average degree, right? So we should actually be able to recover the average degree fairly well in this star subgraph sampling. So this is a pretty realistic setting with two variables where we have one network statistic that's measured with sort of minimal error, the average degree, and the other that's measured with a substantial amount of error, the average clustering. And so as we adjust the sampling fraction, you can sort of see a couple of things here, right? The first is that as you adjust the sampling fraction, it's not it's not totally clear how the sort of the bias in the average clustering coefficient is sort of fairly substantial and positive for sort of most values of the correlation of the sampling fraction, but it's not sort of uniformly so. It can be sort of biased in the negative direction as well, which is what we were discussing, since we have this this sort of correlation structure between the actual clustering and the observed clustering is what really matters. And nothing says that can't be dependent on the sampling rate. And in fact, we showed that in the sort of simplified case of scale distortions, it certainly is. So the second thing to point out here is that if you have a coefficient that is measured, even if that coefficient is measured without error, if it is correlated with a coefficient that's measured with error, you could still see substantial bias in that coefficient value as well, right? And so you see here, if the correlation is 0, right, as sort of expected, we do an okay job of sort of estimating the average degree, the correlation between degree and clustering. But if there's an association between a sort of moderate to large association between average degree and average clustering, then we can see both positive and negative biases, and some of these biases become relatively large, order of size of the coefficient and magnitude, even though that coefficient is sort of measured itself without error. So this is just to say the sort of multivariate case becomes kind of even more challenging here. Okay, so under either star or subgraph sampling, you can't consistently estimate beta in the regression that we've been talking about here. You also can't assume the direction of the bias is known. So it's sort of not standard attenuation bias that you might sort of, the kind of thing you might hope for in a setting where you have, mismeasurement that's based on a sort of sampling that's a simple random sample even. So what really matters is the covariance, how what you see varies with what the truth is, the sort of covariance between those two things. And this, this of course is an issue that I'm presenting in the context of regression, but the sort of fundamental, and this sort of previous statement makes this point sort of pretty succinctly that the fundamental issue here is about the statistics themselves and sort of how the sort of statistics, the values of the statistics are distorted under sampling. All right, so that's kind of the situation that we're in. Now, what do we do about it? So this is from Chandrasekhar and Lewis, again, which I would refer you to for the full derivations. But sort of the idea here is that for some statistics, we can actually characterize and correct this bias under the two forms of sampling that we've talked about, the star subgraph and the sort of subgraph, induced subgraph sampling. So if we take a collection of graphs, so again, remember, this is your, the sort of Strava networks of a bunch of people, or a bunch of, sort of classrooms in a school, that type of setting. If we take a bunch of graphs and sort of local and global statistics, we start with something like the average degree, which is, I'm calling a sort of hyperlocal statistic here because it really depends on the sort of the connections that people have, the sort of single link connections that people have. Moving sort of up in complexity and in terms of the sort of higher order properties of the network, to things like clustering, which of course depends on sort of common edges amongst the neighbors, to something like support, which is sort of asking what share of nodes have at least, what share of links have nodes where at least one of those has a friend in common. So now we need to think about not just the edges amongst the neighbors, but the sort of the connections that the neighbors have. And then sort of graph level statistics like average path length and spectral functions. So for all these statistics, we can sort of at least get some direct insights in the sort of induced subgraph and star subgraph context. So I apologize. This is a bit of a change of notation, but will now sort of represent the sort of sampling rate with this notation. Okay, so in subgraph sampling, for the local statistics, we have a couple of sort of nice sort of results, and again, these are sort of fully spelled out and justified in the Chandrasekhar and Lewis paper that I referenced before. For degree, we can sort of simply rescale by the sampling rate, and this is sort of consistent with what I sort of was describing before. This idea that you might expect that as we sort of trim the number of individuals, we might be sort of trimming the number of potential edges that you could have, that any one person could have, in a sort of relatively proportional way. The degree of clustering, we can use that estimate directly. That again is going to sort of depend on the sort of the size of the induced subgraph in terms of the accuracy of that estimate, but that at least is sort of, we are sort of at least preserving some information under sampling there. For the support, however, there's really no simple solution in terms of how you estimate the support, and that sort of makes sense, right? Because if you think about sort of in the sort of induced subgraph, what you're really kind of losing here is what you're really losing here is precisely what you need for support, which is about the sort of the fraction of links where the sort of the nodes involved in those links have a connection in common. So you're really not getting any opportunities in the induced subgraph to sort of observe those sort of high order properties. Now moving to the sort of the star subgraph. Moving to the sort of star subgraph, you sort of do need to do a minor correction on the degree, which again sort of would make sense given the design, right? Because you are you sort of observing the edges of amongst people who are sampled, but you still are missing some of those potential edges that individuals might have. So there is a correction with that. Same thing for clustering, a correction that depends on the sampling rate. And so for support, yeah, so this is actually, yeah, this is a sort of not finished bullet point here. You're going to use the sort of the I and J sampled nodes, and essentially what you're going to try to do is you're going to try to estimate a potential distribution from the I and J sampled nodes, and then sort of use that as a correction. So there's kind of a two-step process there with support. But the key piece of information there is that you can at least sort of adjust back to an estimate of support with the induced subgraph, or sorry, with the star subgraph. Whereas with the induced subgraph, you don't really have any information to try to estimate what support is going to look like. Okay, so this is sort of a set. Again, I'll sort of refer you to the Chandrasekhar and Lewis paper for full details here, and then just kind of move on to the sort of global statistics and the spectral functions. In terms of the global statistics, so the path length, and this is the average path length. The intuition here is that is sort of what I alluded to earlier, which is that in the subgraph, it's going to look like the average path length is longer than it actually is. And that's just because you're sort of thinning out a bunch of edges. So you're essentially sort of removing a bunch of the really short paths that would be, that you would be otherwise observing. And so when you go to compute the average, you're looking at something that looks bigger than it actually is. So there is I didn't put this in here because it's a bit involved. There is a sort of direct correction, again, based on the sampling rate in the sort of work by Chandrasekhar and Lewis that I refer you to if you're interested in that explicit form. And in terms of spectral functions, the sort of eigenvalues, and so we know that the eigenvalues can are sort of really important in terms of understanding things like the sort of interpretations of sort of diffusion in the graph and that sort of thing. So, and if your goal is to estimate the eigenvalue, so this lambda 1 here is the sort of first eigenvalue of the adjacency matrix itself. So if your goal is to estimate that, then there's not a direct form, but there is this kind of this what I think is a sort of fairly hopefully kind of a bit intuitive structure here, where your estimate of the first eigenvalue in the star subgraph, and here's another less than or equal to right there. So you're going to underestimate the first eigenvalue if you use the star subgraph, and you're going to even more severely estimate the first eigenvalue if you estimate if you use the induced subgraph. And that sort of makes sense in terms of the kinds of paths and the kinds of sort of diffusions that you might be able to observe across these two methods of sort of thinning out the graph based on sampling. Okay, so outside of a few statistics where the correction's tractable, so what do you do? And so these are all settings where you have sort of collections of graphs as well. And so if you have a single graph, what can you do? So one solution is to assume a parametric model for the graph, estimate the parameters of that parametric model, and then use those parameters to generate missing links. And so then resampling graphs from the estimated parameters yields a distribution over the statistic of interest. So basically, we sort of assume a parametric model, estimate those parameters in the parametric model, use the model parameters to generate graphs, and then every draw from the sort of parametric model distribution gives us a statistic of interest. And so the key thing here, the key sort of insight here, which I will sort of illustrate in one specific example in a minute, is that even though it might not be possible to estimate a specific parameter from the sample, but it might be possible to estimate the parameters of a generative model that are preserved under sampling. And that's sort of not true in all with all generative models, and also not true depending on sort of the sort of transition, sort of how the sampling is happening. The sampling of the nodes is happening, but at least for sort of a class, a sort of broad set of parametric models, we might reasonably expect that even if the specific features of a graph are not possible to estimate with the sample that we have, that a sort of broad class of distributions, or the distribution over the graph, might be able to be sort of relatively precisely estimated. Right, so we can't tell exactly, for the graph for the sample graph, we can't tell exactly the number of triangles, for example, but we might be able to tell, what distribution that graph came from, and then from that distribution, we can simulate graphs to infer a distribution over the number of triangles. That's the idea. So this graph reconstruction approach you can do in both the subgraph and star subgraph cases, but I'd like to sort of switch to a slightly different example for the last piece here. And the sort of the key idea here is this sort of one of the sort of classic trade-offs in sort of statistics, right? Which is, that we can assume, we can make assumptions about the parametric model, and then we need data to estimate the parametric model. But then with the data to estimate the parametric model, we can sort of estimate a sort of broad set of parameters on the graph, and then therefore sort of regressions from those parameters. Or we can defer making those assumptions about parametric models, and if we defer those assumptions, then we're left with sort of specific statistics on sort of collections of graphs that we can use. So this is really the sort of trade-off, right? We can make more assumptions, and that allows us to sort of work in a more flexible space, in a sort of more efficient way, assuming that we're okay with those assumptions, or we can sort of forego assumptions and work in a sort of restricted space where we can come up with tractable forms. So I want to give one example of the sort of the framework, the sort of more parametric assumption focused framework, which is using something called aggregated relational data. And so this is essentially a way of asking people how many connections they have with a particular group of individuals, right? So it might be sort of how many people with a particular name do you know? How many households do you know that own a particular piece of farm equipment? These are sort of examples from one survey that uses this type of data collection. So in a sense, this is a sort of extreme example of sampling where we're going to sort of have a sample of nodes, and from that sample of nodes, we're going to ask them not about connections to specific individuals, but about connections to groups of individuals. And so the idea here is to go, we're going to process exactly the sort of setup that I just described. We're going to take our data, which are these ARD responses. We're going to use those to estimate formation model or sort of generative model, statistical model parameters. From those models, we can generate graphs, and from each of those graphs, we can get a graph statistic. And in the end, we'll sort of run a regression, which is sort of very similar to the one that which is the sort of setup that we discussed before. Which has to do with your sort of outcome, which is a sort of health or social or economic outcome, equal to some function of beta times the network statistic. Okay, there are many sort of caveats here, but I'll kind of defer talking about most of those for the purpose of illustration. But again, I'm happy to kind of dive into those a bit further. Okay, so the sort of formation model or the probabilistic model that I'm going to assume is what's called a latent distance model. And this latent distance model has been used sort of widely in the networks literature. So the sort of an early reference to this latent distance model is a paper by Hoff, Rafferty, and Hancock from 2002 in the Journal of American Statistical association. And the sort of idea here is that we're going to take the dependent structure in the network and we're going to represent that in a low-dimensional geometric space. And so what we're going to wind up with is we're going to have a setting where the probability that person I and person J connect to each other is going to be proportional to GI and GJ, which are the popularity of person I and the popularity of person J. And then a term here, which is going to sort of essentially give us sort of extra propensity to form connections based on these sort of latent positions of person I and person J. And so what we'll wind up with is we'll wind up with a sort of setting here where we have this low-dimensional space, and we're essentially having distance in this low-dimensional space represent the propensity to form ties. So here we say that this person J is more likely to form connections with this person than they are to form connections with this person, right? Because the distance between these two is smaller than the distance between these two. And this is advantageous because it allows us to essentially use the geometry as one of the parts of the model. So here, this is a sort of two-dimensional flat surface. And so, we can make triangles. And so we know that from properties of triangles, if I know how far apart these two individuals are and how far apart these two individuals are, then it tells me something about how far apart these two are. And the key assumption here is that we have conditional independence sort of given the latent position. So if I know the positions of the individuals in this space, then I can model the probability outcomes here as a sort of set of conditionally independent, essentially sort of Bernoulli coin flips. Okay, so the goal here is going to be to estimate these parameters, to estimate the parameters of this model. And then once I've estimated the parameters of this model, I can use this sort of probability statement, and it's appropriately scaled. I'm writing it here as a proportion to make this to make the exposition a bit simpler, but it is sort of appropriately scaled in the end. I'm going to use this formation model to sort of generate graphs, right? I can generate edges here, so I can sample graphs over and over again. Okay, so for respondent I and group K, so group K here means like the number of people with a particular name that you have, or the number of people that you know who own a tractor. I observe what I'm calling YIK, which is the sum over all the people in the group of whether or not I have a connection to that person. And so again, conditional on these latent positions, we have that this YIK follows approximately a Poisson distribution, with the mean of the Poisson being just equal to the sum of these probabilities of knowing each person in the group. And so again, the sort of conditional independence assumption is really critical here, because it means that we're sort of adding up a bunch of sort of conditionally independent, and you'll notice these are sort of not identically distributed. So we might sort of more appropriately represent this with a sort of Poisson binomial distribution, but the sort of Poisson approximation works pretty well in practice. And these are all sort of relatively small probabilities. Or sort of mostly relatively small probabilities. So we're sort of, the sort of addition here is over to these conditionally independent binary outcomes with relatively similar, with sufficiently similar success probabilities that a Poisson approximation is reasonable, at least in practice. So we can observe this. If we actually observe the positions of everybody, if we actually observe the connections, we could sort of do this computation directly. But we don't actually do that. We don't actually observe the positions, because we just know, remember, how many connections you have with a group with a particular type. And so since you don't observe these connections, you approximate this this term here, this mean, by essentially replacing a summation with an integration component. So instead of having a a sum across all of the people and the latent positions of all the people in a particular group, all the people who own tractors. I'm essentially just gonna take the sort of expectation of one of those people, and then multiply it by the number of people in that group in K. So once we do that, that's really the big connection, right? That's how we get to a likelihood. So this gives us a likelihood, and I'm not showing the details, but it turns out that it's a likelihood where we can. This term doesn't seem like it would be would produce a tractable mean for the Poisson, but it actually does. After a sort of nice bit of algebra, you wind up with a Poisson distribution that has a tractable mean parameter and can be estimated with a sort of standard tools. So what we're going to do is use these sort of ARD questions. How many people do you know of a particular type, to estimate the model parameters, and then sample graphs from this model, from this formation model. For each draw from the graph, we're going to compute a statistic, and then our sort of eventual estimate will incorporate that variability across draws from the same graph. And again, just to sort of to remind you, we're not observing any links in this setting. The model that we're using is this model here. So I'm claiming that I can use the how many people do you know type data to estimate the parameters of this model. And then, thanks to the sort of conditional independence assumptions that are inherent in the formation model, I can sort of estimate these model parameters. Then once I have model parameters, I can just take draws from the distribution, essentially flipping the coin with the sort of corresponding probabilities, and then end up with a set of graphs, and then for every graph compute the statistic, and then my sort of ultimate sort of uncertainty interval for beta incorporates those samples across the graph, across simulated graphs. Okay, I'm not sure why this is taking a long time. All right, well, okay, so just to sort of show you an example of how this works, this is sort of network data from work by Banerjee et al. 2016. It's near complete network data from about 16,500 households across 75 villages in rural India. There's also these aggregated relational data collected on about a 30% sample. So what we're going to do here is we're going to compare the estimated coefficients in a regression from aggregated relational data with the coefficients that you obtain and have been previously published in the economics literature using these sort of 16,500 households to the complete graph. So the idea here is to sort of build on previous work about sort of peer-driven financial institutions, and so these are sort of areas primarily that don't have access to sort of formal banking, and what that means is that sort of your peers, your network, sort of serve as as sort of stand-ins for lots of these institutions. So if you need a loan, you're likely to ask a peer as opposed to go to a bank. And in this context, this idea of sort of social reputation really matters, right? So if you come and ask me for a loan, one of the ways that you can sort of be more assured that I'm going to pay the loan back is if you know that we know lots of people in common, and if I don't pay the loan back, then I'll get a bad reputation as a person who doesn't pay loans back. Oh, apologies for that. That's just there. So what do we have here? We have a regression where, so this is an experiment, and the sort of idea of the experiment is that a person is asked, a person is asked if they would like to save money, and they make a commitment to save a particular amount of money, and then a monitor is randomly assigned throughout the network. So some other person in the graph is assigned as the monitor, and the monitor receives periodic updates about whether or not the person is reaching their savings target. There's no sense that the monitor should do anything, they're not sort of instructed to sort of try to help the person save, to sort of coach them in any way. There's no sort of instructions about an intervention of the monitor. It's all about information. And so the theory here, based on sort of previous work in economics, is that that both the sort of centrality of the monitor and the centrality of the sort of saver should really matter. So centrality should matter. So you might imagine that that a monitor who has the ability to tell many other people about your reliability or lack thereof with respect to your savings targets, that person is going to be more effective in sort of encouraging you to, it's going to produce more incentive to reach your savings target than a person who's sort of on the periphery of the network and can't really tell that many people. Similarly, the proximity of the monitor should matter. So somebody who knows, who's very close to you in the network, should be sort of more, should produce more incentive to reach your savings target than somebody who's far away in the network. And so it should be a sort of the sort of combination of these two things, the sort of centrality and proximity, are represented in this QIJ statistic. And so then we run a regression where the outcome of the regression is the amount saved by person I is just equal to beta Q ij plus epsilon. Right, so the outcome here is the amount of money that you save. The right-hand side variable is this QIJ, which has to do with the centrality of the monitor, of the saver, and of the proximity between the monitor and the saver. So if you do this regression using the full graph, what you wind up with is a positive coefficient, which means that if you're randomly assigned to someone who is more central and more proximate, then even without instructing that person to intervene at all, what you wind up with is a setting where a person with an assigned monitor who is more proximate and central in the graph is likely to save more on average. So a positive coefficient here means more saved. So this is using the full network. So this is using the full graph of connections. If we look at the ARD case, we get a coefficient that's of course not exactly the same, but is substantially overlapping and provides the same substantive insights as if we had the full network data. So moving on for one more example here, this is a case where we have a sort of outcome on a beliefs-based outcome. So this is sort of looking at sort of responsibility. So the outcome here is the monitor's belief about the saver's responsibility. So this is like, sort of at the end, you sort of ask the monitor if they, think that the saver is the person that's saving money is responsible. And this is important because this is the sort of key outcome, right? So if we're sort of thinking about informal interactions, and one of the things that really matters is your reputation, measuring, did people who are randomly assigned more central monitors, were they perceived as being more responsible? And so again, same thing. So this is the full data estimate, and again a positive coefficient, which is sort of telling you that those more central monitors perceive the people they were monitoring as more responsible, which is sort of which again is sort of the randomization is important here, right? Because it's not that they're selecting more responsible people. It's that people that they're